Everyone, it's my pleasure to welcome Patrick Gaulme from the Institut d'Astrofísica Spatiale in Orsay to the IAC today to talk to us about some of his work, a lot of which involves observations done here on Observatoire del Teide. His talk is in support of his application for the generic postdocs, and I think he'd personally find his work very interesting, and I hope you will as well. So without further ado, Patrick.
Okay, thank you. So I'm here to talk to you about the study of a planetary system, which was done by CoRoT, a French European satellite, and for which IAC people were involved, Hans and Clara. And as some of you and as Brandon told, I'm here also because I applied to a postdoc position here. And so I will shortly present what I did and what I'm currently doing, because this is a pretty recent work, but published in the late 2010. And also last week we were in Marseille with Brandon, Hans, and Clara, and where I presented a new result that I obtained with my Nice collaborators on Jupiter and Jupiter seismology. And we thought that it would be a good idea to present it shortly. So actually it will be a two-part seminary instead of one seminary. So it will be 40 minutes in total, don't be afraid. Just before, so I'm French. I did my PhD in Meudon several years ago. Then I worked 2 years in the Nice Observatoire in the François-Xavier Schmider team. And then it's been 3 years and a half that I'm in IAS, working with Thierry Apourchot and Marc Olivier mainly. First on the inner structure of planetary, of giant planets of the solar system by using seismology. And now it's been 3 years that I'm working on stellar system, in particular with CoRoT and Kepler data. So actually I had a mouse, which would be a pointer. I don't know where it is. Okay, it's there. Okay. Let's start with Jupiter. Jupiter is the biggest planet of the solar system, as you may know. It represents almost 70% of the mass of the whole of the solar system by excluding the sun. And it's a planet which received a lot of visits, 7 flybys by space probes, and a dedicated orbiter. And the next NASA mission is dedicated to Jupiter. It's called Juno, and the launch is in August. And the only solar system planetary mission from the first phase of Cosmic Vision program of ESA is dedicated also to Jupiter with the mission EJSM, which is now called JUICE and maybe one day Laplace. So what do we still ignore about Jupiter, despite of all these visits and the proximity of the planet with respect to us? It's the deep internal structure. And knowing and constraining, bringing new constraints on the deep internal structure would allow us to constrain several questions. And for example, high pressure physics, the equation of state of matter at very high pressure, in particular the hydrogen and helium. And also for the mechanism of formation of the solar system, and the probing to probe the deep internal structure, the core region of Jupiter, would allow us to know if the planet formed by accretion or gravitational instability. So the current knowledge of Jupiter is a 4-layer model with basically a core region made of ices and rocks, and then a huge metallic envelope, mainly of metallic hydrogen envelope, and then a molecular envelope made of principally of hydrogen and helium. And then the last layer is made of, it's called the atmosphere. Actually, it's almost all atmosphere, but it's the region where you have the clouds and where you have the 3-layer clouds. So on the plot, actually it doesn't work anymore. Yeah, it's not so important. The plot on the top, this plot shows the mass of the core as function of the mass of heavy elements in Jupiter. And, okay, it's from different models, and I won't detail all of the models. Practically, they use different, use different equation of states. And what is important to notice is that the core mass can be 0 or can be 15 Earth mass. So it's a big uncertainty. And the idea of doing seismology of Jupiter emerged in the late 70s because as a natural extension of solar helioseismology, because the common fluid nature of the two bodies leads to similar oscillations, P modes typically, and similar techniques to search them for. So the frequency range and the amplitude are of the same order of magnitude as the solar oscillations. So from around the millihertz frequency, so from 5 to 30 minutes of period, with amplitudes of from 10 centimeters per second to 1 meter per second. And several attempts were done in the 80s and 90s to search these oscillations with not specific instrumentation. And if thermal infrared photometry didn't give any result, Doppler spectrometric measurements from Schmieder and Moser showed ambiguous results. So maybe I forgot to mention that all of the data in asteroseismology are analyzed in the Fourier transform of the time series. So these are the power spectra of the time series obtained by Moser and Schmieder. And you see an excess power in the expected region. But there were, at the time, no way to demonstrate that it wasn't a systematic signal from the telescope, for example. So Jean-Guay and François-Xavier Schmieder developed a new concept of instrument. It's a Fourier tachometer, such as a gong or MDI for the sun. Actually, it's a Max Zehnder design, and it was used twice during two campaigns in 2004 and 2005. And so this is the instrument. You see there, it's a Max Zehnder interferometer. You have Jupiter in the entrance. You have 4 images in output. And by a linear combination between the images, you got the interfering pattern, so the fringes. So you have fringes overimposed on the image of Jupiter. And the basic principle is to measure the velocity field in the upper atmosphere of Jupiter by measuring the light shift of the interfering of the fringes. So after subtraction of their instrument response, we got the fringes parallel to the rotation axis. And so we measure the rotation of Jupiter, the very fast rotation of Jupiter, which is one of the main limiting factor for doing observation of seismology of Jupiter, because the rotation is 25 kilometers per second from one side to the other side of along the equator. So it introduces a strong jitter noise. So with this instrument, we can remove the rotation of Jupiter because it's a well-known rotation. So the best data set was obtained here at AAC with the Carlos Sanchez telescope in 2005. It's a 9-day run, 7 nights on a 9-day run. So with a duty cycle of about 20%, 23. So with a high daily aliasing, but with good condition here during the acquisition of data. 3 years ago, we published the instrument performance, which are about 12 centimeters per second for the noise level in the power spectrum, which was 5 times better than previous observations. And at the time, no global feature of the oscillating modes were put into light. These are the L-new diagram, such as for helioseismology. And actually, we don't see anything. At the time, we focused on the spurious signals, on the different sources of spurious signals. And we put into light noise due to thermal drifts, due to guiding of the telescope, to atmospheric effects, and to the coupling between the mass we use. So we decided to reanalyze data by focusing only on the data, on the time series, associated with, on the best time series. And so I forgot to mention that so each velocity map is decomposed in the spherical harmonics base, and And so actually the best spherical harmonics are associated with the degree L equal 1 and with only antisymmetric masks. So the power spectrum of the data associated with the L equal 1 masks leads to this plot, where you see here the frequency expressed in microhertz, and here the power in centimeter per second square. The red curve here indicates the noise level, and you clearly see two excess power between 800 and 2000, and a secondary excess power before 3000 and 500 microhertz. So it looks like a lot to what we were expecting from Jupiter's oscillations. But it's not a demonstration that these are oscillations. So the first thing we did was to, and the other interesting point is that, okay, we have excess power, but we have also a kind of regularity, a comb structure of peaks, which strongly reminds the solar or stellar oscillation modes. So the first thing we did was to estimate the mean large spacing from autocorrelation and to find a separation of 155 microhertz. And then we built the Echelle diagram. The Echelle diagram consists of dividing the power spectrum. If we have a regular signal in the power spectrum, we divide the power spectrum in small pieces, small intervals of 155 microhertz in our case, and then we stack one piece over the other. And so if we have alignments, we see some patterns in the folded power spectrum in the diagram. So this is the diagram, the Echelle diagram of our data, and you see alignments of peaks here, but also here. And the secondary maximum excess power that we saw actually mirrors these effects. You see also they are mostly aligned. This has to be compared with the HD, it's a CoRoT star, HD 181906. It was published by Rafa Garcia. And you can see that the similarity between the Echelle diagram with the same kind of signal to noise. You have to know that this star is an oscillating, a pulsating solar-like star. It's not the best one, but it's not the worst one. It's just an average oscillating star. And so the main difference between the two plots is obviously the daily aliasing for the ground-based observation of Jupiter. So, okay, and then at last we studied the possibility of other explanations to explain what we are seeing. So first of all, we know that we have thermal drifts of the interferometer and that we have also guiding noise. So we compare the power spectrum in the range clearly dominated by thermal effect, clearly dominating by telescope guiding, and in the observed excess power. And we see no correspondence at all in the autocorrelation of the power spectrum in these three regions, so we can rule out these reasons to explain what we are seeing. So another explanation could arise from photometric features, because Jupiter is a very complex planet. It has a very confused structure. It's not like the Sun, which is almost flat. We have a lot of clouds, different structures, regularity, periodicity. So it could explain something. But SIMPA is designed also to circumvent this problem. We have the images of Jupiter. So we processed all the time series of the images of Jupiter in the same way as the velocity maps. And we see that the power spectrum is really different. We have no regularity in the power spectrum. We have a totally different structure. So it can be also ruled out. And at last, we could imagine that solar modes could be visible on Jupiter. Because actually we use the Sun, we use Jupiter as a mirror. We do some Doppler measurements on solar line. It's actually the magnesium triplet at 517 nanometer. And we'll use these lines reflected on Jupiter to measure the Doppler shift. But as I told you before, we consider here only the antisymmetric masks. So any global signal arriving on Jupiter is just cancelled out because you have a negative and a positive part, and they compensate, and so the average is 0. So they could not be visible. But in case of leakage, because of imperfect correspondence between the mass and Jupiter, we plotted the Herschel diagram of the same data with the large spacing of the Sun. Obviously, the solar modes are not high in the main excess power around 1,000 microhertz. So it could explain the secondary excess power, but even in the secondary excess power, we don't recognize the classical two-ridge Herschel diagram which is observed on the Sun. So the only explanation that it remains is that the signal is from Jupiter, and from Jupiter you can have only one explanation. It's the global P modes. So at last we compared. We cannot. I just like to tell that we cannot do identification of the modes because of the daily aliasing and the leakage between the mass. It would be dishonest to try to tell, okay, this peak is L equal 2, M equal 1, because actually it could be even L equal 0 or L equal 4, because we have leakage. It's not possible to, at the time, to identify. But we have a good value, a good estimate of the large spacing, of the mean large spacing. So we just compared with the help of Tristan Guillot, who calculated the models of Jupiter, the theoretical values of the mean large spacing here as function of the mass of the core. And 4 different models, so each color indicates a different model. So what we see first is that actually the mean large spacing, which is proportional to the mean density, is not sensitive to the core mass. Very slightly sensitive to the core mass. It's not the good parameter for that. But we can see a strong correspondence because the gray line, the gray region indicates the region where it's our value, it's our observation. And you have to think that both values are totally independent. We didn't use any model to estimate our value, and they didn't use any of our inputs to determine these models. It's from equation of states and abundance in the upper troposphere. So you can notice that these 4 or 5 crosses, black crosses, represents values of the large spacing and the core mass for former models from the 90s, where they use a pretty big approximation for the equation of state of heavy elements. And so these more approximated models don't fit with our observation, which is a first step, and it's a good information. And in the estimate, in the core and in various models of Jupiter, the squares here, the bottom line of each model actually, indicates models with a pure ice rock core, while the upper line is made of pure rock core. And we see that we have the tendency to slightly favor pure rocks core than a pure ice core. But the signal to noise is too low to be certain about that. So for this work, is the first detection, first clear detection of Jupiter's oscillation, even if we had some previous tentative detection during the 80s and 90s, is thanks to the ability of SAMPA to manage to have the spatial and frequency resolution. And so it opens a new window for the investigation of internal structure of the planets of the solar system, because it could be applied to Saturn, Uranus, and Neptune. And so for this, we proposed to put a dedicated payload on the EJSM project, ESA mission. It's currently an IAS Observatoire de la Côte d'Azur project. It's led by the 2 institutes, and this is the design of the instrument. It inherits from SAMPA, of course, which can be seen as a prototype of this instrument, and also on the from the techniques from Gong and MDI from Soho. So I finish now with and yes, these results are currently in press in astronomy and astrophysics, and they are available actually on AstroPH archive. It's been 3 days. So now the study of the planetary system, HD 46375. It's a work which we started 2 years ago almost. And the idea was it was the only exoplanet previously to the launch known in the core field, in the core eyes. And it's a Saturn-like planet orbiting a solar-like star. And the idea from 2 groups, from Hans Degg and Clara Regulo here, and Tristan Guillaume, Martin Vanier, and Suzanne Desgrains, was to observe this system with CoRoT, with the seismic field of CoRoT, because it has higher cadence, 1 image per second instead of 1 image per 32 seconds, and it can have access to brightest stars. So the idea was to search for the phase change of the planet along its orbit, even if it doesn't transit the planet. So you will see the planetary system like that, inclined, tilted by a given angle, mostly for 45 degrees, and we looked for the phase changes. And the ideal idea was to also detect the oscillations of the star to better constrain the system, and also to have a ground-based support which was simultaneous to the observations. So the star is an uninvolved K0 type with a high metallicity. Most solar-like stars observed by CoRoT at the time were mainly F stars for oscillating stars, I intend. And few G and early K stars were observed from the ground base, also with CoRoT. And so it's 8 magnitude with a temperature on the surface of about 5,200 degrees, 1 solar mass, a bit less, 1.9, with an age estimated at the time at 5 gigayear, and so pretty high metallicity. The planet has a M sin E of 0.22 Jovian mass with semi-major axis of 0.04 AU, a small eccentricity. And what is interesting is the main problem of all the analysis of all the data set was the proximity of the period, which is 3.02 day with 3.0 day. And you will see after that is the main problem of this target. So by supposing an inclination of 45 degrees of the star and the radius about between a range around 1 Jovian radius, we expected the flux variation from 0.4 to 27 ppm, 0 to peak variations. So I start briefly with the ground-based support, which I did not realize. It was done by Jean-François Donati and Claire Moutou with the NARVAL spectro-polarimeter at Pic du Midi Observatory. And the idea was to monitor the magnetic activity and maybe to determine the period of rotation more accurately, and to have an idea of the whole magnetic field structure. So they confirmed that it was a very quiet star. It's a very quiet star with almost no activity. We don't see any. So the run was 35 nights in parallel with CoRoT observations. They had, in the end, 17 spectra, so pretty good coverage. And they don't see any periodicity in their measurements. So because it means that the rotation period of the star is longer than 35 days. And from this observation, we also learned that the magnetic field has a globally dipole structure and is different from the other planet-bearing stars observed with this instrument, but it's mainly because it's a slowly rotating star, while the other planet-bearing stars were a fast rotator, pretty fast rotator. And from the same data set, we were able to fit the lines because it's a good, it covers all of the visible, with a high resolution, and so it allows us to get the global parameters as the temperature, log G, and the high metallicity. It's actually almost 0.4, and the V sin I. So here is the CoRoT light curve. As you see, it's 34-day, and we would like to see a kind of periodicity, but actually the run is too short to be certain that it's due to the rotation. The main information here is that it's indeed a very slowly low active star, because the peak-to-peak amplitude are about 400 ppm, which is very low compared to other oscillating stars observed by CoRoT. So the pros and the cons of having a quiet star, it's okay. You can tell, okay, it's better because we could see easier. It will be easier to detect the planetary signal. But actually, the problem is that it's slow, slowly rotating, low active, so it's totally impossible to do some spot modeling, for example. So we cannot model the activity of the star. So actually, it's more difficult to disentangle the planet from the activity of the star. So this is a representation of the same in the power spectrum. And so people doing asteroseismology see that it's a very quiet star with a smooth profile. It's a log representation of the power spectrum. And at the time, in this moment, we don't see any excess power indicating the pulsation of the star. But actually, when taking a look at the smooth power spectrum, we see a very small excess power here and maybe there. And so we looked for not to detect directly the peaks of associated to the oscillations, because they are too low amplitude. But another, I would say, trendy method, which is currently used, is to look for the large spacing signature in the autocorrelation of the time series. Actually, in the filtered autocorrelation of the time series. That is to say, we calculate the autocorrelation of the time series by using the Fourier transform. So we take the Fourier transform of the time series, and we multiply the Fourier transform and the conjugate of the Fourier transform, then go back to the time series. And in the Fourier domain, we can put a filter to filter out the frequencies where we don't expect the modes, and we can repeat the operation by centering the filter in different positions of the power spectrum for different frequencies. And so in the end, we got this diagram where we have the autocorrelation as function of the time, and for different filters centered on different frequencies. And we see here a clear excess of power. It corresponds to this excess power here. And applying a statistical test, a null hypothesis test, it turns out that actually it's not noise at more than 99.9% of a rejection level. So we have an estimate of the mean large spacing, which is not so much. We cannot detect any variation of with a good confidence level of the large spacing. And however, it allowed us to model, to constrain better the model of the star. So with the new values coming from the spectroscopic ground-based support here in input, and coupled with the large spacing value, we got a new model. And so the values are not so different with before. The mass is actually higher, pretty higher, and the age is divided by a factor 2. But the most important thing is that the error bars are reduced by a factor 2. So we can see that even with a poor oscillation detection, we just have the mean large spacing, we can actually reduce the error bars on the stellar model by a factor 2. So after we looked for the planetary signal in the light curve. So by taking the power spectrum of the time series, we expect the planet in this range, in the gray region, and we don't see anything at all. The question is that on 34-day, the frequency resolution in the power spectrum is 0.34 microhertz. So in the same bin, in the same frequency bin, we have actually 3 days, 3.0, actually really 3 days, and the period of rotation of this planet. So by supposing that we have systematic signal at 3 days as a multiple of the Earth rotation, and we know that CoRoT has a strong spurious signals at 12 hours and 24 hours. So they could interfere, and reduce interfere and destruct the amplitude of the peak here. So it's not, because we don't see anything there, that we don't have anything. So we folded then the time series. The advantage of the folding of the time series is to take into account the phase information, because by considering only the power spectrum, we cancel out the phase information, because the ephemeris are pretty good and accurate, so we can compare the folded time series with the ephemeris. So the red curve here indicates the ephemeris, and the black dots the measurements. So we see actually an agreement between the values here, but excepted in this region where we have this huge peak of an undetermined amplitude. So what is it? Actually, we try to see that it could be a spurious signal. So we compared this time series with another. We looked for another quiet star in the same detector on the same field in the same time from the same CoRoT dataset. And actually, among the other stars, there was only one star which is actually quieter than this star, but all of the other stars were variable stars with amplitudes of several thousands of ppm. So this other star is indicated in red, so it's with a small amplitude, smaller variations with respect to our star here. And so we folded also this time series with the same way on the planetary period. And so this is the expected signal. This is the this is the data of HD 46375, and this is the folding of the other star. I forgot to put the error bars, but they are of the same order of magnitude of the other star. So we don't see very common features, and what is interesting is that the kind of sign trend here is not present in the other star. But it's not very significant, and so we plotted the folding of the time series, of the 2 time series, on 3 days, not on 3.02, but on 3 days. And we see there a very strong correlation between the 2 data sets. So it indicates that we have a regularity of 12 hours, actually not 24 hours, because it's different from this peak to this peak. But we have a 24 hours periodicity in this CoRoT dataset. It's probably due to the low orbit and the crossing of the South Atlantic anomaly. And you may know that even on SOHO data, we see the Earth rotation while it's on the Lagrange points. We always have the Earth rotation. So the misfortune of this planet is to have this rotation, the period of orbiting, which is very close to 3 days, and to the systematic signals. We try to apply the systematic removing from Maze et al., but actually it's for exoplanetary field, and it doesn't work. It doesn't reduce the signal, the standard deviation of the points. So the only thing we could do was to basically filter the reference star time series by considering only the frequency range where we are working, and subtracting this time series from the dataset. And so it's interesting because we see on the left before, so the folded time series of HD 46375 with the peak here, and on the right the same thing after subtraction. And you see that the amplitude of this strange peak is reduced by almost a factor 2 with respect to the sign trend. So the sign trend is enhanced by this operation. So it would indicate that indeed this peaks is spurious remaining from the rotation of the Earth. But actually, the only way, and that it's positive, and we think that it could be indeed, we have a signal compatible with the presence of the planet. But we cannot now demonstrate that it's definitely not a spurious signal. So the only way to go further is to reobserve this star on a longer run in order to have the sufficient frequency resolution, so you can distinguish in the power spectrum 3 days from 3.02 days. And so we would need ideally 120 days, but actually 90 days would be good enough to spread out, to smooth the effect of this peak if it's from terrestrial rotation origin. So it allows us, this study can be seen as a kind of prototype of Plato-like observations, so with a combination of asteroseismology and also exoplanetary science. And it puts into light to see the possibility of detecting planets without transits, which would enhance a lot the quantity of planet to be detected with a mission of like Plato. And it also, so the asteroseismic analysis coupled with the ground-based support allowed us to refine strongly the parameters on the age, on the inclination, and finally on the mass of the planet, which is 0.3 Jovian mass, more or less, less 0.05 and more 0.14. And if the signal that we detect is from the planet we are searching for, it would correspond to, by supposing that the radius, it's from models, is about 1.1 Jovian radius, and that the inclination is 45 degrees, which is very close to 50, which is the best estimate. By supposing it's due to only reflection of stellar light, it would imply an albedo of 0.16 to 0.33, which is pretty high. But 0.16 actually would be good, fits with the other detection. And if it was only due to the thermal emission of the planet, it would imply a warm planet, 2000 K, which is too much for us. So it's not so close to the planet, and the star is not so. So actually, it could be also a combination of the two effects. So I've finished with that. And I'd just like to give you a short summary because of what I'm doing now, because since I'm applying to a postdoc and I have no intention to work alone here, it's just 3 slides to tell you what I'm doing now. And it's Bayesian modeling applied to stellar systems, so to CoRoT data. And basically, it's on solar light spectrum and exoplanetary curves. Because in front of the huge amount of data, mainly because of Kepler, not CoRoT, and of the faintness of the signals that we are searching for, we need to develop some new methods to analyze the data in a statistical way. So first of all, I developed with Thierry Bourchot a code which is totally independent from the other existing code, which detects the presence of oscillations from the autocorrelation time series, and then it automatically fits model the low frequency trend of the power spectrum, and at last it fits the oscillating spectrum from the star with 2 possible models. It's on the mode identification associated with different peaks. And after it compares the 2 models in terms of probability in order to get the best model in terms of probability. And at last, it's also able to detect mixed modes by dividing the power spectrum by the models and to detect the remaining peaks. For example, here, after the division of the power spectrum with the model, you see clearly that we forgot one peak, which is probably a mixed mode. And now, more recently, I'm working on exoplanetary stuff in particular to the detection of very faint signals. Because the problematic is that if you have, for example, you see the primary is from Snellen et al. On CoRoT 1b, was the first detection of phase changes of an orbiting exoplanet, and also of the secondary transit. And the idea, okay, it's pretty clear here. You see the transit, and you see the phase changes and the secondary transit. But it's not always so clear. For example, here it was observed, it's another star, WASP-19, observed by A-STEP in Antarctica. And you see here at the time of the secondary transit, a very slow, very low depression, and maybe a kind of symmetrical trend around the potential secondary transit. But how can we claim the detection here of the secondary transit? Actually, the only way to do it is to apply the Bayes theorem, which allows us to calculate the probability of a model. Okay, you hesitate between two models, so we detect or we do not detect the secondary order effect, such as the secondary transit. The only way to say, okay, we have found it, is to calculate the probability of the model associated, including the secondary effect. And on the other side, to calculate the probability of the model excluding this effect. And you can actually have more than two models. You can have 3, 4, 5. And in the end, we compare the different models in terms of probability. So that's all. I finished now. And if you have some question, I would be glad to answer.
Thank you very much, Patrick. Questions, anyone?
Could the method that you've just displayed now in the last slide be applied to detect non-transiting planets in Kepler data, which is something that was proposed by Jenkins and Doyle? And Jenkins will, by the way, be there tomorrow. But is that a possible application of your work?
Yeah, actually, it's one of the things that I would like to do, because after having worked on this CoRoT data with the non-transiting planet, I think in the Kepler data we should search for such kind of effects. Actually, it's very difficult to say, okay, we have detected it. And I think Bayesian approach is mandatory. Yeah, we could surely apply this. To give any probability. It's pure noise. It's a sine trend. Okay. Which probability? Yeah, we surely can.
You don't know a priori any period, because in a planet search you don't.
Yeah, we ignore everything. Yeah, I know. But we still do. Okay, we can search for in given ranges, because okay, we won't search for very fast or too long periods. We can put some prior. We could put some priors on the search. Yeah.
Anyone else?
Totally unrelated to the begin on Jupiter.
Yes.
One thing, maybe that is totally outdated by now, but what I thought is an option is that Jupiter has also a metallic hydrogen core. How does that fit in with either being rocky or ice core? Is that included in one of the two options, or is that something that's not considered any longer?
Yeah, in the two cases, in all of the models you have metallic hydrogen, and maybe I don't remember of all of these models, but I think most of them predict phase transition from molecular hydrogen to metallic hydrogen with a discontinuity. And it's not visible on this. It's the same, we actually, to constrain the internal structure of Jupiter, we have to identify the modes and not just the mean. The mean value gives mean parameter. So to go further, we need some individual frequencies. And that's why we want to reobserve, maybe, and from ground-based, it would be better from space, surely.
Maybe what's understood under pure eyes, maybe to clarify that. Is that water ice you're talking about? To the lower right in the box, it says
Here?
pure rock. No, to the lower right in the text, pure rock, slightly favored. I know what you mean by rock, but slightly favored with respect to pure ice. Is pure ice water, or is that then what you mean by metallic hydrogen?
No, it would be, it would suppose that basically it's in the formation of the solar system, you suppose that you have a planet, a protoplanet of several Earth mass, which is made of ices. Mainly, mostly water, actually. Yeah. Yes, and it froze the gas, and then accreting the hydrogen. But it could be water, CO2, or other frozen gas.
Yes, Theo Roca. I wonder, in the case of the Jovian seismology, I'm not convinced that you've seen any mode at all. And I would rather think on seeing first the sun. I understand on the Jovian line.
Yes.
I understand that you cannot see it because you make the difference.
Yes.
And so you have you lose that signal. Having the four signals, the four images,
Yeah.
There is not a possibility of keeping the sun signal.
Actually, the problem with the sun signal, I told that, okay, it should be cancelled out because of the antisymmetric mass, and also because we don't see any signature of the typical solar mode, such as the large spacing in the power spectrum. But there's another point, is that actually solar modes are really in the noise level of the power spectrum. Because when I speak about here a 12 centimeter per second of noise level here, actually it's by considering it's a noise, it's a velocity sensitivity, 1 sigma velocity sensitivity, by considering that the Doppler shift is magnified by a factor 2 because of the reflection, because we are working on solar reflected line on Jupiter. So if you have a motion on Jupiter, the effect is magnified by a factor 2. So actually, it means 12 centimeter per second on Jupiter is actually 24 centimeter per second. And we know that solar modes are about 15 to 20 centimeter per second per mode. So it should really lie in the noise, and we don't expect to see such peaks. And if we translate the height of these peaks in velocity for Jupiter, so taking into account the magnification of a factor 2, and also taking into account daily aliasing, which reduces the amplitude of the peaks, we would obtain peaks of about 50 centimeters per second. So in terms of solar, supposing they are from solar origin, it would mean 1 meter per second amplitude solar modes, and in the 1000 region, which is not the maximum. Actually, the solar modes are here. Okay, so this could fit with solar mode, and maybe they are solar modes, but so we are sure that these first peak are not solar mode. The secondary peak, I would not be so certain. We have strong indication indicating that they are not. But we cannot exclude it because actually it fits with the main frequency range of the solar modes, and maybe we have some, we don't know why, but we don't know why. This is the point. And I have to remember at last that the Jovian modes, the cutoff frequency of Jovian modes is in this range. So it's absolutely not abnormal to have Jovian modes at such frequencies. So we don't think it's